Howdy, this is the solutions video for section 1.3D homework. We're on page 65 and the assignment's 57 through 68. So let's get to it. All right, our first one is the limit as x approaches 0 of sine x over 5x. This one is even easier than the example problems we did because I can just pull out a 1/5 there. 1/5 times sine x over x. That's the exact same thing as this. And we know the limit then would be 1/5. And this is one of our identities, sine x over x. So that's 1. So that answer would be 1/5. Okay, 58 is the limit as x approaches 0 of 3 times 1 minus cosine x over x. So that's almost the identity we need. That'd be the same thing as the limit as x approaches 0 of 3 over 1. I'm just going to pull that 3 out. Times 1 minus cosine x over x. So that's 3. And then 1 minus cosine x over x is equal to 0. 3 times 0. And that is 0. Sometimes I have students actually do 3 times 0 is 3. So be careful. Don't do anything like that. Okay, the next one, I'm going to go ahead. Number 60 is not real big, so we'll go back and do 59. 59 takes up a little more space. Let's do 60 real quick. Limit as theta approaches 0 of cosine theta tangent theta over theta. All right, let's change that tangent to sine over cosine. So we'd have cosine theta times sine theta over cosine theta. I hope you can see something useful is about to happen. So those cosines will cancel out, and you've got the limit as theta approaches 0 of sine theta over theta. And that's the same as sine x over x, right? So the answer is going to be 1. All right. So let's back up and do 59. Which takes a little more manipulation. So we've got the limit as theta approaches 0 of secant theta minus 1 over theta secant theta. So if we plug 0 in, we're going to have 1 minus 1, which is 0, over 0 times 1. That's 0 over 0. So let's change secant into cosines. So it's going to be 1 over cosine theta minus 1 over theta over cosine theta. Okay, since secant's 1 over cosine, then if you multiply theta times 1 over cosine, you get theta over cosine theta. Now I'm going to change that 1 into something more useful. How about 1 over cosine theta minus cosine theta over cosine theta? That's a clever version of 1, isn't it? But it allows me to put that fraction together. So that's the limit as theta approaches 1 of 1 minus cosine theta over cosine theta over theta over cosine theta. Now I'm going to flip this bottom fraction and multiply it. Sorry about that. Theta approaches 0. That's 1 minus cosine theta over cosine theta times cosine theta over theta. Now the cosines cancel. and we'd have the limit as theta approaches 0 of 1 minus cosine theta over theta. Well, that's just this identity right here. We've just replaced the x's with the theta, so that is 0. Lovely. That's a good algebra problem there. Love having to rewrite the number 1 as something more clever. Okay, number 60. We've got the limit as theta approaches 0 of cosine theta, tangent theta over theta. The limit as theta approaches 0. Let's change that tangent into sine over cosine. So we'd have cosine theta times sine theta over cosine theta over theta. Cosines will cancel, and you have the limit as theta approaches 0 of sine theta over theta, which there you go, it's same as sine x over x. That is equal to 1. Beautiful. All right, 61. We've got the limit as x approaches bagel of sine squared x over x. All right, let's pull that sine squared apart. So the limit as x approaches 0 of sine x over x times sine x over 1. If you multiply that back out, you're going to get sine squared x over x, right? So we just pulled the sine x. Now it's not sine x over x again, because if you multiply it out, it'd be x squared. It has to be sine x over 1. Well, we know that that is 1. And then if you plug 0, sine of 0 is 0, so times 0 over 1, which is 0, so that would be 0. Boom! We are cooking. All right, 62. So tangent squared x over x. Okay, anytime you see tangent, think, maybe I'll change it into sines and cosines. So sine squared x over cosine squared x over x. And then I can bring that x on the bottom right up here. Whoop. So that's the limit as x approaches 0 of sine squared x over x cosine squared x. All right, that's a 2, but it looks terrible, sorry. Okay, sine squared. Now that's not sine 2x, that's sine squared x. Okay, let's see if we can break this bad boy up. So the limit as x approaches 0, how about the top we just write as sine x times sine x? That's the same as sine squared x times x times cosine squared x. I really don't need to break that up. You can if you want, but you don't really need to. So the limit as x approaches 0, let's break it up. Sine x over x times sine x over cosine squared x. Now I think we can plug in, because sine x over x is 1. And then that's going to be, if you plug in 0 for sine x, that's 0. But if you plug in 0 for cosine, that's 1. So it's 1 times 0 over 1. That's why I didn't have to write that out twice. I knew the cosine of 0 was 1. So that's 1 times 0, which is bagel. All right, lovely. Okay, just, I'm not sure I got room for 63 down here. It's not a super long one, but. Okay, 63. We've got the limit as h approaches 0 of 1 minus cosine h all squared over h. Okay, that gives you 0 over 0. Let's rewrite it so it looks kind of like this guy. We've got the limit as h approaches 0 of 1 minus cosine h times 1 minus cosine h. That's the same as 1 minus cosine h all squared, right? Over h. Now I wonder, how about we can rewrite this limit as h approaches 0 of 1 minus cosine h over h times 1 minus cosine h over 1. Now it's not over h again, it's over 1. Remember, if you multiply that out, that gets rid of the 0 in our denominator because we know this is the same as this, so that's 0. And then I'd have 1 minus 1 over 1. So that's 0 times 0 over 1, which is 0. Awesome. Okay, I think I can smush 64 in here. We got the limit as phi approaches pi of phi secant phi. Well, secant's 1 over cosine, so that's the limit as phi approaches pi of phi over cosine phi. So that's going to be pi on top, just plugging in pi for phi. Cosine of pi is -1, so that is negative pi. Boom. So that's really pretty much a plug-in. If you knew secant of pi was -1, then you could just plug that straight in. But I went ahead and changed it to cosines in case you didn't want to think too hard on that one. Okay, we are more than half done. Got to do 65 through 68. (65) is the limit as x approaches pi over 2 of cosine x over cotangent x. Now, just the fact that it's not as x approaches 0 means we're not going to end up using one of these identities. So, it is 0 over 0, but let's see if we can cancel some things out here. So first of all, let's change cotangent. So you have cosine x, and cotangent's cosine x over sine x. And then that allows us to go whoop, like that. So that's the limit as x approaches pi over 2 of cosine x over cosine x times sine x. Well, what happens to the cosine x? Wah. And so I've got the limit as x approaches pi over 2 of 1 over sine x. Well, what's the sine of pi over 2? It's 1. So that's 1 over 1, which is 1. Okay. Well, I need some space for number 66, so I'm not going to be able to squeeze that joker in. There, let's see if we can. There you go. Okay, number 66. Probably the hardest one of the bunch, and there probably won't be one this quite this hard on the test. So, but it's still, you want to work some hard ones. So x approaches pi over 4. So we're not going to end up using any of these identities because they're all x approaches 0. So this is going to be a pure algebra manipulation problem. 1 minus tangent x over sine x minus cosine x. Okay. You plug in pi over 4, you're going to end up getting 0 over 0. So let's first change that tangent to sine over cosine. So 1 minus sine over cosine over sine x minus cosine x. Okay, let's rewrite that number 1 a little more cleverly. How about cosine over cosine? So we've got the limit as x approaches pi over 4 of cosine x over cosine x minus sine x over cosine x over sine x minus cosine x. Okay, so then I'd have cosine x minus sine x over cosine x. So I was able to put those two fractions together now that we have a common denominator over sine x minus cosine x. So we can bring this guy up a level, doink. I've got the limit as x approaches pi over 4 of cosine x minus sine x over cosine x times sine x minus cosine x. Now I hope you remember from just a few lectures ago how you can factor out a -1 and reverse the two numbers. So let's factor a -1 out of the top. That is a great algebra trick. So we're going to factor out a -1, and then it's sine x minus cosine x. You get to flip the two as long as you factor out a -1. If you don't believe me, distribute the negative sign. It'd be negative sine plus cosine, which is the same as this. So over cosine x times sine x minus cosine x. All right, well, what happens here to the sine x minus cosine x? Wah. So I've got the limit as x approaches pi over 4 of -1 over cosine x. That's going to be -1. You know that cosine of pi over 4, you know, you get to use your unit circle here, but cosine of pi over 4 is root 2 over 2. So that's going to be, you can flip the bottom, if it's -1, -2 over root 2. That is fine with me if that's how you leave the answer. But if you would multiply that by root 2 over root 2, to rationalize it's -2 root 2 over 2. The 2's cancel, and you'd have -root 2. I don't remember how the back of the book puts it, but on the test, I'm totally fine with leaving a radical in the denominator. I do not get bent out of shape over that. Okay, by far that's the longest one of the homework. The next two are not that long at all. So 67, we have the limit as t approaches 0 of sine squared t over t squared. We can rewrite that. Let's just break the sines and the t's up. The limit as t approaches 0 of sine t over t times sine t over t. That's the same as sine squared t over t squared. Multiply those two out. Well, we have an identity for that. It's 1. We have an identity for that. It's 1. 1 times 1 is 1. Easy peasy. Okay, our last one, number 68. The limit, this is like a lot of those homework examples I did, as x approaches 0 of sine 2x over sine 3x. So what you're going to do is let's break these up so that we can insert the numbers we need. So sine 2x over 1 times 1 over sine 3x. Well, what do we need here on the bottom? We need a 2x so that it looks like this. So 1 over 2x. And then what do we need on top? 3x over 1. Now what have we multiplied the whole thing by? 3 over 2, 3 halves. So I've got to compensate by multiplying by what? If I multiply the whole thing by 3 halves and order it to be the same equation, then I have to multiply by 2/3. Because this is the same. This whole thing is just multiplying by 1, isn't it? Which is totally legal. So let's rewrite this as the limit as x approaches 0 of sine 2x over 2x times 3x over sine 3x times 2/3. So I just pulled that 2 right there, pulled that 3x right there, just put them together. So we know that's 1 because we have an identity right here. This is 1 times 2/3. Don't forget about that. That is 2/3. All right, that does it for this solutions video. And I will talk to you next lecture.